Assalamualaikum. Three-phase induction motors are very commonly used industrial motors, and in today's lecture we shall study the construction and working of three-phase induction motors. So three-phase induction consists of a stator. On the stator we have set of three-phase coils which are placed 120 degrees from each other for the case of a two-pole machine. And these coils are supplied with three-phase currents. So the stator of a three-phase induction motor is exactly the same as stator of a synchronous motor. The rotor of three-phase induction motor, that is generally cylindrical. On this rotor there are bars of conductors placed in the notches which are carved along the surface of this rotor. So we have multiple conductors placed on the rotor. These conductors are placed on the notches which are carved along the surface of this rotor. The rotor is of ferromagnetic material and is laminated to minimize the hysteresis and eddy current losses. These bars are then shorted to each other with the help of shorting rings, both at the front end and as well as at the back end. These bars are shorted through shorting rings. So if you look at the rotor from the side view, it should look like this one. We have a cylindrical rotor with multiple bars placed on it. Bars of conductors. So these bars of conductors are placed on the rotor, and at both the ends these are shorted by shorting rings. Here is a shorting ring and here is another shorting ring. This is not the only type of rotor which is there in three-phase induction motors. This is the simplest one, which is called cage rotor. There is another type of rotor which is called wound rotor. In case of wound rotor, the winding on the rotor are just the mirror image of windings on the stator. That is corresponding to this coil. There will be one coil over here corresponding to this coil, and likewise corresponding to the third coil there will be a third coil on the rotor. And this has the advantage of low cost. The wound rotor is more expensive and is less commonly used. However, this wound rotor has an additional advantage. That is, we can modify the torque speed characteristics with the help of torque speed characteristics of this three-phase induction motor with the help of wound rotor. We shall talk about that thing in the later lectures. Next, we talk about working of this three-phase induction motor. So when three-phase currents are supplied to these coils, set of three-phase coils placed on the stator of three-phase induction motor, a rotating magnetic field is produced. So that rotating magnetic field is denoted by Bs. This speed of rotation of this stator magnetic field, that is related with the frequency of the voltage which is supplied to these stator windings. And for a simple two-poles machine, which is depicted over here, the speed of the rotation of this stator magnetic field, that is equal to the frequency of the applied voltage. And if you have more number of poles on the machine, then we have this relation. This frequency is related with this speed of rotation in this way. And if you represent the speed in revolutions per second, then this speed is given by this thing, where Fe is frequency of this signal, this voltage signal in hertz, which can also be written in this form, which is equal to 2 Fe over P. And here this speed is in revolutions per second, cycles per second. This is something mechanical quantity, and we are more convenient if we represent the speed in revolutions per minute. So we know that if Fs is revolutions per second, then 60 times 60 multiplied by this thing will be revolutions per minute. So speed of this rotating magnetic field, that is equal to 2 multiplied by 60, which is 120 Fe over P. So this speed of rotation of the stator magnetic field, that is called synchronous speed. This is the speed at which the rotor of a synchronous motor will rotate. So how is torque induced in this particular motor that will rotate the rotor? Let's elaborate that thing with the help of figures. On the rotor, we have these rotor windings, and due to stator windings, we have stator magnetic field. This stator magnetic field is rotating with synchronous speed. And this rotating magnetic field links with these conductors, and we know that when a conductor is placed in a magnetic field and there is a relative motion between conductor and magnetic field, voltage is induced. That induced voltage is given by this relation V cross V dot L, where V is relative velocity of conductors relative to this magnetic field. So due to relative motion between conductors and this stator magnetic field, voltage is induced in these conductors. And since these conductors are shorted through shorting rings, therefore current will start flowing in these conductors. For this particular time instant, this is the plane of maximum voltage. That is, maximum voltage will be induced in this plane, because here the stator magnetic field is maximum. And current will flow in these conductors. Direction of current in these conductors can be easily determined. We know that this is ds, and relative velocity, this magnetic field is moving in this direction. So this is linear velocity of magnetic field, and velocity of conductors relative to this magnetic field is in this direction. So this is velocity of conductor, and V cross B is out of the surface of board in this particular situation. So in these conductors, this will be the direction of current in the conductors. We also know that this rotor circuit, that is behaves as an inductive load, and therefore the current in these conductors will lag behind the voltage. That is the time instant when voltage is maximum in this particular current. The current will become maximum in this conductor after certain time. So here is the plane for maximum current in the rotor of this induction motor. And direction of current in other conductors can also be determined. Due to this current in the conductors, there will be a magnetic field. Direction of magnetic field can also be determined. Current is entering in these conductors and leaving in these conductors. So here is the direction of rotor magnetic field. And now, due to interaction of these two magnetic fields, a torque will be induced, and that induced torque is given by this relation. This torque will be induced, and that will cause the rotor to rotate. The direction of induced torque will be such that it will tend to align both the magnetic fields, Br and Bs. Bs is rotating with synchronous speed, this rotor will also rotate. This is the same phenomena which occurs there in the damper windings of a synchronous motor that we have already talked about. Remember that for this three-phase induction motor, rotor will not rotate with synchronous speed. It can reach to near synchronous speed. However, it will not run at synchronous speed. Why? Because if the rotor is rotating at synchronous speed, and you know that this stator magnetic field, what is speed of rotation of stator magnetic field? That is also equal to synchronous speed. Speed of rotation of stator magnetic field is equal to n sync. If this rotor is also rotating with the same speed, there will be no relative motion between the stator magnetic field and these conductors, and hence no voltage will be induced in these conductors, and therefore no current will flow, and hence there will be no rotor magnetic field and hence no torque. So if rotor rotates at synchronous speed, induced torque will become equal to 0, and hence the rotor will slow down. So for an induction motor, rotor does not rotate with synchronous speed. It can achieve near synchronous speed, however it does not rotate at synchronous speed. Therefore, we define a term for the case of induction motors which is called rotor slip. There is a difference between speed of rotation of rotor and speed of rotation of stator magnetic field. So we define slip speed. Slip speed is the difference between the two speeds, that is synchronous speed minus speed of rotation of the rotor of this induction motor. And we also define another thing which is called a slip. Slip is defined as synchronous speed minus speed of the motor divided by synchronous speed. And if we are interested in percent slip, then we just multiply it by 100 to give percent slip. What we can see is that for synchronous motors, speed of rotation of rotor is always equal to the speed of rotation of this stator magnetic field, that is equal to n sync. Therefore, for synchronous motors, this slip is equal to 0. And for the case when this rotor is stationary, how much will be slip? The difference percent slip will be equal to 100%. This is 0, so 1 divide this n sync divided by n sync multiplied by 100, that is equal to 100%. The slip corresponding to the situation when rotor is locked, that is 100%, or slip is equal to 1. Percent slip 100%. For an induction motor, slip is always between 0 and 1. We can also rearrange this equation to write it in this form as well. Speed of rotation of motor is related to synchronous speed with slip, or in terms of radians per second, then speed of rotation of motor, that is given by this relation. This is a brief introduction to the working of three-phase induction motors. In next lecture, we shall talk about torque speed characteristics of three-phase induction motors.